delay. So Rolf Hagedorn, as you see here, in his office in about 1978, was a particularly important man for the many of you who are involved in the heavy ion physics. And one way to keep a field on physics alive and in the right place is to remember the people who have helped create it. Because in the end, it is we are the descendants in an intellectual way, one way or another, of the people who have been there before. And sometimes it's wise to remember that one stands on the shoulders of giants. Who is the giant is not always as obvious as it may seem, because in his time, Hagedorn, in the early days, wasn't really recognized as a giant of science. In actual fact, if I know how to turn the page, thank you. So this reminds us first why we're here, before I start talking about a few things about Hagedorn. So Hagedorn temperature is festivity, is this evening, this afternoon, 50 years of Hagedorn temperature. Everybody knows Hagedorn temperature? More or less. It will be explained 5 times this afternoon. Now, what is perhaps less known and less obvious to many young people is that Hagedorn's activities have actually paved the way for the development of a heavy ion program at CERN. In my opinion, and I was witnessing this as a young man, there's no question about it. And the reason is very simple, that Hagedorn was attracting young scientists who came to CERN to study hot hadronic matter. Hagedorn's hot hadronic matter. That's very simple. So there was always a flow of people who came and went. Some of us were fellows, some of us were on short-term appointments. And so for that reason, he created the tradition and which today is, I would say, roughly 25% of the CERN scientific program. So how did it come to be is a very interesting footnote in history. So this is the appointment letter of Hagedorn to a permanent CERN position. I should point out that Hagedorn came to CERN before CERN was created. CERN was created after Hagedorn joined CERN. So in other words, he took upon himself the risk of coming to an institution which was yet to be built. And in the 1960 permanent appointment letter, Hagedorn is charged by then Director General Adams with the task of to use statistical models for predicting particle production and otherwise to follow the developments of particle physics. And so he lived up to this charge for the following 43 years of his life. He took it very seriously. If those of us who know Hagedorn know that for him, this was like a command, I will do this. And he did. And the other thing is what you should know about the situation is that Heisenberg, as of course Helmut Zatz reminded me many times when I always forget, had this hobby of studying cosmic stars. The emulsion stars, when cosmic rays come, explode and target nucleus. And he hired Hagedorn, who was a student of Becker, and some of you who are educated in Germany know who Becker was. His book is the standard of education in thermal physics. And so Hagedorn was the student of Becker hired by Heisenberg and then sent to CERN to do thermal particle production. And Adams confirms this a couple of years later, appointing him to the theory division, to permanent position, to do just that. And so Hagedorn does. And 50 years ago, not to the day, but within months, he invents what we today call Hagedorn temperature. It is the same year in which quarks are invented. It's the same year in which Higgs proposes the Higgs particle. It's the same year in which the Big Bang, Penzias-Wilson happened. It's the year which created the science of today. 64, 65, the 12 months are quite remarkable. I mean, if 1905 was a year of wonders because of Einstein, 64-65 certainly was the next great breakthrough in the understanding of our science today. Now, however, the Hagedorn temperature had a birth which was not exactly easy. The first paper, of which you see here the preliminary version, which is dated 12 October 64, is in essence suggesting that Fermi-Dirac statistics is not to be followed precisely, because in order to have the right hadron spectra, you had to make particles distinguishable. And obviously, this didn't sit very well with some of the colleagues of Hagedorn, and Hagedorn decided to withdraw the paper quite soon after that, and so we were in limbo. This paper lingered in archives. I had a copy. Some of his Hagedorn friends had a copy, but it was not made public until recently. Now, then, shortly after withdrawing his paper, Hagedorn has the brilliant idea that there just may be, there is a way to save the situation, in that one can invent a theoretical model which has so many different particles that the particle distinguishability is natural, that each hadron is different from the other. He built such a model and discovers the exponential mass spectrum. So in other words, the number of particles of a kind grows exponentially, and the exponential is called Hagedorn temperature. So there is the invention, and that is the paper which is dated 25th of January 65, which is well cited and has turned around the field of particle, at least to some of us, of particle physics, and this is how, of course, the spectrum was exponential indeed, as you see here. And Hagedorn proposes a power law with prefactor 5½ but in actual fact, as we later learn, it's at least 3, if not 7½. So the story is not finished in 65. There's lots of work which follows, and obviously some of this will surface in other lectures, but this introduction will now go to where I enter this game is 10 years later. We work on hot hadronic matter. This is a phase diagram which we drafted around 1978, 79, which is later, which has a very nice appearance. As you can realize, it is not very different from what we believe in today, but it shows in essence how hadrons evolve into the different components which are there. We have a slightly different view of it 30, 40 years later, but this is what it was, 980. Then, around the same time, a strangeness happens. I have the pleasure of being asked with Hagedorn to give a lecture in GSI by Rudolf Bock, and the charge letter explicitly says to us, you must produce an observable of quark-gluon plasma. You don't need to come talking about quark-gluon plasma unless you have something to say about how to look at it. It was not so rude, but it was what Bock said. And we obliged, and this created the strangeness as an observable, and it ultimately also led to the creation of a wide field of research at CERN. This is a program of research which we had at CERN, which was set up by the committees between 80 and 86. You'll see many experiments. In following years, RHIC was developed, quite remarkably, following in the footsteps. A few years later, notice please that the program at CERN was started 80 and was finalized in 86, and the program at RHIC started 94 and came on in 2001. And then this is my favorite observable. It works. Emanuel Quartzig is here to confirm that the largest medium effect in most characteristic signature of quark-gluon plasma are indeed strange antibaryons, at least for the moment. Now, year 2000, we have quark-gluon plasma discovered at CERN. Here we are. I remind you, this is still online. You can check it. CERN stands by its official story of discovery of quark-gluon plasma. And, of course, there is another announcement of quark-gluon plasma discovery 3 years later or so, where on 18th of April 2005, we will hear more about this discovery as well later today. We have coagulum plasma, two labs discover coagulum plasma in different signatures within a few years of each other. And, of course, what do we do today with it is the big question. Do we have any use for coagulum plasma today? So my perspective, the interesting aspect is how to connect the collision of which we have in laboratory, here depicted in this picture, with the interesting context of early universe. And we learn by looking a little bit around that there are differences and similarities. We have the ability to explore the early universe, but there are some serious differences, so therefore the conclusion is that theory connects the heavy ion collisions to the early universe. I'll show you one picture which I love a lot. This shows you how the universe looked as a function of time, and here you have the rapid change in evolution, all the particles changing rapidly within a time frame which is a few tenths of microseconds. And then there's evolution which contains neutrinos, electrons. When we see baryons come back to life, all this has a much, much, much longer time scale. So the riddle of how the universe evolved is all in the first, I would say, millisecond of its lifespan. And I would like to close the short introduction by showing you Hagedorn, the last really public lecture of Hagedorn. This was at a meeting in '94, where we asked him to give again. So I remember vividly how this evolved. I asked Hagedorn, would he like to lecture at the time that we celebrated him, and he was 75, if I remember correctly. And Hagedorn said he has nothing new to say. And I talked to him, think about it. And then suddenly he came back and he said, yes, I actually have something to say. I have something to say how the thermal model came to be. Not about how the statistical bootstrap model was invented, because he said, and coagulum plasma phase transition. I gave this lecture in '84, he said, in Helsinki. What I didn't tell the story about is how the thermal model came to be. And this is such a wonderful talk which he gave and which is written up extremely well in the corresponding proceedings. If you want to know the history of a thermal model, the history which gave birth to coagulum plasma, you read this article. This is the legacy of Hagedorn as one can see it. And we, of course, reprinted it in the book, so this is, now we'll see greater circulation. But it is very important to realize that Hagedorn both described the discovery of Hagedorn temperature and coagulum plasma proposals in his '84 Helsinki lecture, which is also in the Hagedorn book. And then he ventured even further to write up precisely the startup of thermal models. Thank you very much, everybody. Thank you very much, Urs, for letting me give this lecture.
Okay. So, Jan, thank you very much for this teaser. What I suggest, we will have several speakers. We have a discussion forum at the end. What I suggest, we regard this at the moment just as a teaser. We will come up presumably to all the aspects you have mentioned. We start with the other scientific talks, and we take then questions after each talk, except if there are very important questions already arising now. But otherwise, I would suggest we thank Jan for this teaser, and we go right away to the next